Swayam Prabha. Digital India. Educated India.
Welcome back to our lecture series on advanced hydraulics. We are in the third module on varied flows. Last class we had briefly mentioned on the gradually varied flow and how to classify it. We have not completed the portion on classification of gradually varied flow. So, we will continue that classification of gradually varied flow in today's lecture. So, if you recall in the last class we suggested about the dynamic equation for gradually varied flow using section factors and conveyance factors. So, I hope you recall them, the section factors and conveyance factors. So, this is your conveyance factor, these are the sections factor for critical flow as well as for non-critical flow. All those things we had described it in the last class. In this way you can describe the dynamic equation for gradually varied flow. So, the dynamic equation, it gives you the slope of the water surface profile. We also suggested you what is meant by critical slope, that is regarding the bed slope of the channel. If you recall the bed slope of the channel, for any channel, the bed slope, it can be considered as a critical slope, it can be considered as a mild slope, also it can be considered as a steep slope, horizontal slope, adverse slope. All these things we had described it in the last class. So, today we will see what are the other things, especially in the last class we suggested you in the dynamic equation. In the dynamic equation, one minus z c by z whole square. So, these things in this equation, for dy by dx to be positive, the criteria for that we had discussed it in the last class. That is for breakwater for the backwater, for example, backwater curves, how the if the numerator is positive, then the denominator also have to be positive, or if the numerator is negative, then the denominator also have to be negative, like that. Those things we had described it in the last class. Now, in today's lecture we will see how will the conditions be for drawdown curves. You can simply answer them. Just recall the last class thing, how we describe it for the backwater curves. Similarly, for drawdown curves, what are the conditions? That is, you require dy by dx is equal to negative. Therefore, the conditions are one minus k n by k whole square. This should be greater than 0 as well as 1 minus z c by z whole square. This should be less than 0. This is one criteria. Similarly, another criteria is 1 minus k n by k whole square. This should be less than 0 and 1 minus z c by z whole square. This should be greater than 0. If these two conditions are there, then you will get drawdown curves. The gradually varied flow. For the gradually varied flow, the water surface profiles will give you drawdown curves. So, these then what are the physical meaning of these conditions? Let us consider the case 1. Your case 1 is, say, 1 minus k n by k whole square. How did I write in the last slide? That is 1 minus k n by k whole square greater than 0, and 1 minus z c by z whole square should be less than 0. What does this mean? So, k n by k whole square, that is 1 minus k n by k whole square, this quantity has to be greater than 0. That implies that your normal depth of flow will be less than the actual depth of flow. Why? Isn't it? Say in the channel, say if this is your normal depth line, then your flow may be somewhere here. This y may be greater than, this is y, this is y n. Not only that, what does this mean here? 1 minus z c by z whole square should be less than 0. That is, this quantity z c by z, it should be greater than 1. Then only this can become negative, isn't it? So, what does that mean? Your y c is greater than the depth of flow. So, this implies, what does this imply? It implies supercritical flow. That is, your flow is now supercritical. Also, let us suggest that your y n is less than y, your y c is greater than y. So, y n less than y c, this will be the condition of the flow, and this gives you supercritical flow. This gives you supercritical flow in a steep channel, right? It gives you supercritical flow in a steep channel. Why? This is a supercritical flow, y n is less than y c, therefore, this is a steep channel. Similarly, in the case 2, one can easily elaborate it. So, 1 minus k n by k whole square, this should be less than 0, and 1 minus z c by z whole square, this should be greater than 0. So, the condition what is coming into the picture here is that your normal depth is now greater than the actual depth of flow, then only this quantity k n by k can become greater than 1, right. So, and from here 1 minus z c by z whole square greater than 0, the condition is that your critical flow should be less than your actual flow depth. So, what does this imply? This gives you that your y n is greater than y, which itself is greater than the critical flow. So, this is, if y c is less than y, it automatically gives you a subcritical flow, and also y n is greater than y c. So, this is a subcritical flow in a mild sloped channel. Okay. Like this you can describe the flow conditions. This is how you give the means you can infer from the relationships given in the dynamic equation. So, just recall the various bed slopes we mentioned in the last class about the critical slope, mild slope, steep slope and all. So, we will just I will again enumerate it. So, the various bed slope. So, if your actual bed slope is 0, if it is less than the critical slope, then this is called mild slope channel, and we give the abbreviated letter M for mild slope conditions. So, if your S0 it is greater than the critical slope, this is called steep slope channel, and we give the abbreviated representation S. So, if your actual bed slope is equal to the critical slope, then such bed slope channels are called critically sloped channels. We give the symbolic letter C. If your actual bed slope is 0, so that is there is no slope at all, they are called horizontally sloped channels represented by H. And if the bed slope is less than 0, they are given as adverse sloped channels, A. Okay. So, now these bed conditions are given, and for any given flow situations, one can easily give 3 zones. Say if this is your channel bed, say for the given discharge, if this is the critical depth, you can, for the considerable reach, you can draw the critical depth line. So, that critical depth line is there, and if the normal depth line is given like this, then this depth is your normal depth, this depth is your critical depth, right. And if you see in such channels, there are now 3 zones. Zone 1, this is zone 1, this is zone 2, and this is zone 3. So, for all the channels we mentioned in the previous slide, we mentioned here the mild slope, steep slope, critical slope, adverse slope, one can easily identify 3 zones of flow there. So, zone 1 represents the region above the top line. So, your top line, it can be either the critical depth line or the normal depth line, whichever case it may be. If it is a supercritical flow, you know that critical depth line is above the normal depth line. So, therefore, the whichever region is above the upper line, that region is considered as zone 1. Zone 2 is the region in between the normal depth line and critical depth line. The zone 3 is given as the region between the bed and the lower line. So, like that you can easily identify 3 zones. So, now based on these 3 zones, why okay, I will just write it for your benefit here. Zone 1, space above the topmost line. So, zone 2, space between critical depth line and normal depth line. Zone 3, space between channel bed and lower line. So, why I am classifying is that your water surface, it can exist in any of these 3 regions. Now, based on the channel slope, channel bed slope and the existence of the water surface in any of this region, you can easily classify your gradually varied flow profiles. So, we are now going to classify the gradually varied flow profiles based on these 3 zones as well as the type of bed slope of the channel. Like that, we are now going to categorize them. So, we have already suggested the mild slope channels, steep slope channel, critically sloped channels, horizontally sloped channels, adversely sloped channels. So, in each of these things, in the mild channel also the water surface may exist in any of the 3 zones. So, we have given you 3 zones, zone 3, zone 2, zone 1. So, we have given you these 3 zones. So, your water surface can exist in any of these 3 zones, even in a mild slope channel or even in a steep slope channel, even in critical flow, and we will ask you what about in the horizontally sloped channel and adversely sloped channels. So, a possible maximum possible classifications one can make is that if I give the zone number as suffix to the abbreviated letter. So, the maximum possible classifications one can infer is M1, M2, M3, S1, S2, S3, H1, H2, H3, C1, C2, C3, A1, A2, A3, like that 15 possible classifications can be theoretically, now you can visualize them, or theoretically, not theoretically, we can say suggest that based on the combinations one can infer 15 possible classifications for the gradually varied flow. Now, let me ask you from these classifications, do the classification A1 and H1 whether they exist, whether such classification is possible, H1 exists, why? Now, the question is why. So, what is your response for that? You now casually think on the thing, you will see that, say consider the horizontally sloped channel. For the horizontally sloped channel, your bed slope is equal to 0. Definitely, you will be having critical depth line CDL that is there available for the given discharge. What about normal depth? So, whether normal depth will be there in the computation? What is your inference in this? You will see that y n is equal to some infinite value. So, there is no normal depth for horizontally sloped channels. It is not possible. So, theoretically it is not possible to get normal depth for horizontally sloped channels. Similarly, for adverse slope channels, if this is your adverse slope channel, you can infer the critical depth line, but y n is not possible in adversely sloped channels. So, just recall your Manning's equation. Your Manning's equation which suggested that q is equal to, okay, I will just change the color for your benefit. So, q is equal to 1 by n a r to the power of 2 by 3 s naught to the power of half. This was the Manning's equation for uniform flow, if you recall that. As S naught is equal to 0 in horizontally sloped channels, your y n cannot be inferred. Similarly, as S naught is negative, you cannot have the root of a negative value and subsequently compute y n, that is also not possible. So, y n is not possible in adversely sloped channels as well. Like that you cannot you can infer the things. So, therefore, in horizontally slope as well as adversely sloped channels, we mentioned that there do not exist any normal depth line, or there is no normal depth for the adversely sloped channels as well as horizontally sloped channels. So, you can easily suggest now there are only two regions or only two zones for flow in such type of channels. Now, they are classified as zone 2 and zone 3. Therefore, in these two channels there exists only zone 2 and zone 3. So, there is no zone 1 in horizontally sloped and adversely sloped channels. So, when you devise or when you consider your classifications of the gradually varied flow, you have to keep these things in mind. So, the most common types of channels, they are mild slope channels as well as steep slope channels. These two are the most prominent one. You can now suggest that, say, a mild slope channel is the one where your normal depth line is above the critical depth line, that is normal depth is greater than the critical depth. So, therefore, you can have, say, this is mild slope channel. So, zone 1 of the mild slope channel, zone 2, zone 3. So, if any of the water surface profiles exist here in these zones, say they can be subsequently considered now M1, M2, M3. Similarly, in a steep slope channel, you will see that the normal depth line is below the critical depth line, that is the normal depth is smaller than the critical depth. You can now easily see, or you can easily classify 3 zones, zone 1, zone 2, zone 3. This is a steep slope channel. You can also give the corresponding water surface profiles, or if the water surface exists in this zone, those water surfaces are considered as S1 profiles. Here in this zone, it is considered as S2 profile, and here in this zone, it is considered as S3 profile. Similarly, in the critical slope channels, critically sloped channel. So, what is the peculiarity of critically sloped channel? Your critical depth line is same as your normal depth line. That is, your critical depth and normal depth both are same. So, then you will see that the region above the critical depth or normal depth line, they are called as zone 1, and the region below that, this is called as zone 3. So, zone 2 is missing in critically sloped channels. Okay. So, therefore, you cannot give. So, water profiles and all, C1 and C3, C2 is not existing in such situations, you will see them. So, adversely sloped channels or horizontally sloped channels, this is C, this is horizontally sloped channels. You will have two regions as mentioned earlier, H2 and H3, adversely sloped channel A. So, A2 and A3. You can also mention, you can also consider channel slopes as sustaining and non-sustaining slopes. These are self-explanatory terms, non-sustaining . So, what does this mean? A channel slope, it is called sustaining if its slope falls, or if its channel slope, or if the bed of the channel, if it falls, they are called sustaining type of channels. If it is not falling, they are called non-sustaining type of channels. So, let me ask you what means, where do you encounter sustaining channels? Out of the 5 classifications we made for the channel slopes, that is critical, adverse, horizontal, mild and steep. Out of these 5, which are the sustaining slope channels and which are the non-sustaining slope channels? Yeah, as it is self-explanatory thing. Non-sustaining or sustaining channels or sustaining slopes, they are seen in critical flow, mild slope channel, mild slope channels as well as steep slope channels. So, for the sustaining channels, the sustaining slopes are positive. The non-sustaining slope channels, so their sustaining slopes will be negative and they are found usually in horizontal and adverse slope conditions. So, let me give you a detailed figurative descriptions. Say, if I suggest that based on the various types of channel flow, how your profiles looks, let us see that. See, let me suggest here, first beginning with the horizontally sloped channels. Let us consider the 3 zones available, zone 1, zone 2, zone 3. So, the horizontally sloped channel, it will look like this. It will have the critical depth line and the bed slope like this. So, there is no water profile. See if I make it in a tabular form like this, just for your benefit, I am just giving it like this. So, zone 1, it will means there will not be any water surface profile in zone 1 for the horizontally sloped channels. So, we can easily suggest now this portion does not exist. In the zone 2, in zone 2 your water there is you can draw the critical depth line, and zone 2 what does it represent? So, it suggests you. So, this is your zone 2 and this is the zone 3 of the horizontally sloped channel. So, your water surface will be like this, somewhere here like this, right. It should exist in the second zone. So, it should be something like this. So, this is called H 2. Okay. That water surface profile is called H 2. Similarly, you will see that if the water surface profile exists in the zone 3, that profile would be something of this form, and you can give this, name this as H 3. This profile can be named as H 3. Okay. So, you can say this is zone 2, this is zone 3, zone 2, zone 3, zone 2, zone 3, the slope channel. So, a mild slope channel. Again, let me draw the bed, say bed may be like this. Your critical depth line is below the normal depth line, right. So, you have 3 zones 1, 2, 3, and in the zone 1, if your water surface profile exists in zone 1, that is called M 1, and it may be something of this form like this. So, this water surface profile is called M 1 profile. Similarly, if in the again you draw the same thing, zone 1, 2, 3, and if your water surface profile exists in zone 2, so it may be something of this following form, and this water surface profile is called M 2, because it is existing in the zone 2 and it is in the following form. So, it is in a mild channel. So, this is M 2. Similarly, for the 3 regions, if your water surface profile is something of this form, it is existing in the 3rd region and it is given that water surface profile is given as M 3. One can easily visualize for the steep slope channels also. For the steep slope channels, this is your channel bed, and for steep slope channels your normal depth line is below the critical depth line, fine, and for such conditions the flow to exist in zone 1. So, here the zones are 1, 2, 3. So, the zones are, so from the critical depth a profile exists like this. Usually a jump occurs from the normal depth line to the critical depth, then a gradually varied flow profile occurs, and this profile is called S 1. Similarly, if there is change in water surface in the zone 2 of the steep slope channel. This water surface profile is called S2. One can easily witness the S3 curve as well. So, S3 will be something of this form. Okay. So, like that for horizontal, mild and steep slope, I have just mentioned it. You can easily think for the horizontal and adverse slope channels. Do I need to describe it here? Okay, I will just briefly show it again. For the critically sloped channel, you will have both the critical depth line and normal depth line as the same, both are same. This is zone 1 and this is zone 3, and whatever water surface profile is there, this is called C1 curve. It is in the zone 1. Zone 2 it is not possible, and in the zone 3 you will see that this particular curve, it is called C3. Okay. For the adverse slope channels, definitely for A1 is not possible, as we have mentioned it earlier. So, I can just omit that portion. In the zone 2, for the adverse slope channels, the critical depth line is like this. So, this is your water surface profile that exists in the zone 2, and it is called A2. Similarly, if it exists in the third zone, this water surface profile is called A3. So, like that one can easily visualize various water surface profiles. So, these are the classifications of gradually varied flow profiles. So, what are the theoretical possible things? Gradually you can have H2 and H3 for the horizontally sloped channels. You can have M1 profile, M2 profile and M3 profile for the mild slope channels. For the steep slope channels, you can have S1, S2 and S3 profiles. For the critically sloped channels, you can have C1 and C3. For the adverse slope channels, you can have A2 and A3 water surface profiles. So, this curve, as you have seen the various profiles, I have just arbitrarily drawn like this. Still, in some situations and all, you will see why the curvature of these water surfaces, one can easily determine, curvature of water surface profiles, how the curve should be. So, this is given by say Professor Srivastava in his book on flow through open channels. He published the book in 2008. In that, he has suggested that curvature of water surface, this is nothing but the derivative of the slope of the water surface, right, d squared by dx squared. Now, based on this value, that is based on the value of d squared by dx squared, suppose if this is a positive quantity, so that is the slope is increasing, in the direction of flow. D squared by dx squared, if this is a negative value, you are having a decrease in water surface slope. So, there is a decrease in water surface slope in direction of flow. So, you can easily identify the expression for d squared y by dx squared. You know dy by dx is equal to S 0 into 1 minus k n by k whole squared by 1 minus z c by z whole square. This you are well aware by this time now. So, the what could be the second derivative? You take any arbitrary dimension channels, or for example, rectangular channel. What happens? You substitute the conveyance factors, section factors for the rectangular channel, substitute that here, derive and again derive it with respect to x. What is the quantity you are going to get? You can do it as an homework and let us see that. Anyhow, I am not going to derive them in this particular class. I am just going to write the final expression. So, d squared y by dx squared as given in Professor Srivastava's book, d squared by this is equal to S 0 into dy by dx 3 times y squared into y n cube, that is normal depth, minus y c cube critical depth, y cube minus y c cube, the whole quantity squared. So, a relationship for d squared y by dx squared has been derived in that particular book. I am just showing it here. Why we are showing it here is that from this one can easily picture various features of the water surface curve. So, let me ask you, your d squared y by dx squared, this will be positive when all, at which all times it can be positive. It can be positive if dy by dx is positive and your normal depth, please look into the thing, your normal depth and y n should be greater than the critical depth. If this is true, then d squared y by dx squared will be a positive value. So, what does that mean? What does that physically mean? It is a backwater curve in a mild slope channel. Second condition I would like to ask you, d squared y by dx squared, this can be positive again if dy by dx is equal to negative and your y n should be less than y c. If this is also true, then also d squared y by dx squared will be a positive. So, it represents a drawdown curve, right, in a steep slope channel. The other thing, d squared y by dx squared is equal to a negative value if dy by dx is equal to negative and y n is greater than y c. So, this represents a drawdown curve in a mild slope channel. Similarly, d squared y by dx squared is equal to negative if dy by dx is positive and yn is less than yc. So, one can easily see these things now. You can also plot dy by dx versus depth of flow using the relationship of the using this particular relationship. Or you can also plot the following thing dy by dx versus y. Say for mild slope channel, it has been observed that, so this is referred from Srivastava's book on open channel hydraulics. Say if I plot dy by dx with respect to depth, say if this is the quantity of 0 depth and 0 dy by dx, this is the origin, then this is the depth of flow. Let us suggest this as the critical depth, let us suggest this as the normal depth, you will see that the quantity dy by dx, it will vary with respect to y in the following form. See, like this it may go, then as y decreases dy by dx goes into the asymptote in the negative direction. So, this quantity is approximately equal to the bed slope as 0. So, you can infer from this figure for larger depth dy by dx is approximately equal to your bed slope. Then zone 1. So, this is your zone 1. So, zone 1 and zone 3, which is zone 3. So, here in the zone 3, the dy by dx curve is something of this form. So, like this you can easily suggest now. Say the dy by dx versus y, when you plotted it, it is understood now that zone 1 and zone 3 are having positive dy by dx. Okay. Zone 3 is zone 2 is having negative dy by dx. So, this is always true, or it is always true in such thing, because from that curvature equation itself one can easily plot it and see them. So, that is zone 2 will be always having a negative dy by dx, or it means that it always assists a drawdown curve. You cannot have a backwater curve in zone 2. Similarly, zone 1 and zone 3, they always assist backwater, means or the raise in the water surface things. So, the flow profiles one can easily visualize, say flow profiles. You can see that the M1 profiles, your M1 profiles, it can be seen, say if there is a uniformly flowing channel and if you construct a dam uniformly flowing mild slope channel, say this is your critical depth line, this is your normal depth line, then the M1 curve is observed in the upstream of this dam. In the upstream of this dam, in the following form, you will see this is your M1 curve. Similarly, you will see M2 profiles in the actual field in region, say if there is such mild slope channel that is either falling into another tank or where there is water, say if and if the depth of water in this tank or in this another channel, if it is below the normal depth line, then your water surface profile will be like this, and this is given as your M2 profile, right. So, these things are observed in the actual field situations. Your M3 profiles, they are witnessed, say in the uniformly flowing channel. If you keep a shutter, if you just close the shutter and just slow means if you just open it for a small portion, water will gush in like this, and this water profile is there. This will be an M3 gradually varied flow profile. Similarly, one can visualize S1 profiles. If there is an obstruction in the gradually varied flow, so this is your normal depth line, this is your critical depth line, the water surface, it will cause a jump and it will come like this. This will be your S1 profile. Okay. So, like this you can see various type of profiles in the actual field condition. So, let me now stop here. Today let us conduct the quiz for the today's lecture, the following portion, and we will continue the next lecture next day. So, for the quiz, just now only we discussed on the thing. If a dam is constructed across a uniformly flowing mild slope channel, describe about the flow profile and its type with a sketch. This is your first question. That is, if a dam is constructed across a uniformly flowing mild slope channel, describe about the flow profile and its type with a sketch. Your second question, do A1 and H1 flow profiles exist? Do A1 and H1 flow profiles exist in theory? Is it possible? And give the reason, whatever, whether if it exists, you give the reason. If it does not exist, give the reason. Specific means we have to give, substantiate it. Now, the next question is, from the expression for d squared y by dx squared as mentioned in today's lecture, infer whether there exist positive values for dy by dx in zone 2 of a mild slope channel. Give reasons. So, all are very simple questions today. You can just answer them in 3-4 minutes and just return back the sheets. So, the solution for today's quiz, you can see that if a dam is constructed in a mild slope channel, normal depth, this is your critical depth line, in the upstream of the dam, you will see the water surface profile racing like this, and this water surface profile is called M1 water surface profile. Okay. So, this is in the mild slope channels. Your next question we asked is, do A1 and H1 flow profiles exist? What is your reason? I hope everyone might have answered this thing. For the horizontally sloped channels or for the adversely sloped channels, your critical depth line exists. Fine. And we suggested that there is no zone 1 for horizontally sloped channels as well as adversely sloped channels. There exists only zone 2 and zone 3. So, whatever water surface profile is there above the critical depth line, that comes under zone 2. So, similarly in both the cases, horizontal as well as adversely sloped channels. And you know why zone 1 is not existing? Because you cannot evaluate normal depth for horizontally sloped and adversely sloped channels. Okay. So, this is the solution for the question. Your third question, from the expression for d squared y by dx squared as mentioned in today's lecture, infer whether there exist positive values for dy by dx in zone 2 of a mild slope channel. You give the results. We had asked you to do that. So, your answer is dy by dx will be always negative in zone 2 of a mild slope channel. In fact, for steep slope channels also dy by dx will be negative in zone 2. That will come you can infer it on your own also, you can verify it. So, dy by dx will be always negative in such situations. So, there will not be positive dy by dx values. So, give what is the reason? You have already drawn that curve. You can just go back to that lecture and show to you. Say in this curve dy by dx versus depth, say below normal depth, between normal depth and critical depth, your slope it is going in the negative direction and it goes to an minus infinity. Below critical depth, the slope dy by dx profile is being shown like this. It is in the positive side. So, these are today's things. So, we have discussed on the classification of gradually varied flow. We will see some more other aspects on this thing. We will also solve an example problem in the next class. Thank you.